Okay, let's see. So we're going to look at some new words here. What do you think these terms mean? Feel free to draw a diagram. So the plan, our objective, you're going to extend your understanding of slope to instantaneous slope. So let's go back to that for funsies for a moment. So your understanding of slope in general is you have 2 points. You draw a line between them. And then, depending on how you conceptualize it, you have some sort of rise over run idea. So you could think of it as the y2 minus y1 over x2 minus x1 idea. You could think of it as the change in y over change in x, however you want to think about it. So, let's go back over here. When we're talking about a smooth curve is just going to be a curve where we can, if we zoom in, it looks like a line. That's an easy way to think about it. So we don't need a formal definition of that yet. We'll kind of get to there. But if we zoom in, it'll look like a line. It's like this concept of locally linear. Now a tangent line. Well, suppose I have some sort of curvy curve like this. So a tangent line would be a line that just touches the curve in one place. So let's pretend it touched right there. That would be a tangent line at that point. Maybe I have a tangent line over here. Tangent line right there. Now, if you think about this, let me zoom in. As I zoom in, see how that's becoming straighter and straighter, the green part? What do you think is going to be true about the green part and the blue part at that what is now ginormous dot? That's for you to think about. Maybe I'll ask a question there. All right. And the other part, vocab-wise, is your secant slope. Your secant slope is exactly what we talked to on the left over there. The secant slope is simply the slope between 2 points. So if I drew a line between these 2 points, see if I can hit them, that would be, the slope of that line is the secant slope, and that line is the secant line. So we've got tangent line. The tangent line is like the orange line or the blue line, and the secant line is the purple line. The secant slope is the slope of that purple line. There's also the tangent slope, which we'll probably be talking about a little bit. Now let's see. So we're going to review some stuff first. It says find the slope between the 2 points. Well, a couple different ways to think about it. Many of you might say I'm just going to do 1 minus 4 over 0 minus negative 1. And that's going to be negative 3 over 1. Some of the rest of you, I got thrown off by the scale there. I'm assuming some of you did too. Some of the rest of you will just say, well, I just go down 3, 1, 2, 3, and over what looks like 2, but we're actually going by halves, so over 1. So negative 3 is our slope. Hopefully that part's not too scary. I did give us what the function is, that f of x, and I bet that will come into play in a moment. All right, so now it says leave negative 1, 4 where it is, move 0, 1 closer. What's the new slope between the 2 points? So we're going to have the point negative 1, 4. And we're also going to have negative 0.5, comma. And when you go through, you get 2, which I guess I could have just picked off the curve there. And so the slope there, now you're going to say 2 minus 4, or 4 minus 2, negative 0.5 minus negative 1. So that's negative 2. Negative 0.5 plus 1 is 0.5, or 1/2. 2 divided by 1/2 is negative 4. Do it again. Okay. Leave, oops, that's a typo. That should be leave negative 1, 4. And move the point to where the x value is 0.75. So we're going to have negative 1, 4 and negative 0.75, comma. That's going to be harder to pick off, so feel free to do that calculation. And I got 2.969, whatever. I'm going to call that 3, just to make my life easier, make the calculations easier. I'm just being lazy. If you have a calculator on you, do it more specifically. That will be better. So again, you could say 3 minus 4, negative 0.75 minus negative 1. So you get negative 1 over negative, over 0.25, or a quarter. So that's negative 4. Now, see we got the same slopes there? That's because I rounded. If I hadn't rounded, it would have been slightly different. So feel free to do that calculation, as I said, with a magical calculator. Okay, so now, hopefully you're thinking about, okay, what are we doing? Why are we doing that? So here I'm asking, okay, consider these points, x f of x, and x plus h, f of x plus h. Now feel free to plot those points in space. So you have x f of x, and for the purposes of this, let's pretend x plus h and f of x plus h. We have x plus h, f of x plus h. We probably should put parentheses around these since these are points. And think of the slope here, the slope between these 2 points. Well, we could set it up as f of x plus h minus f of x all over x plus h minus x. But one moment, look at that bottom. Could I simplify that? Could I just get rid of that and get rid of that? Yeah, you can. So you have an expression for the slope. Now what's happening? What are we trying to do with the value of h? That's for you to ponder. I'm not going to fill in that dot yet, or that blank yet. Okay, now I'll fill in the blank. So we have that f of x plus h minus f of x all over h. So what we're doing is we're taking that point, x f of x. We're taking that point in space that's somewhere beyond it. It doesn't have to be above it, but I'm pretending for now. And what we're doing is we're trying to essentially drag this point closer and closer and closer so that eventually it's all but on top of this. Because if I find the slope of the line between the 2 points that are basically on top of each other, that's going to be the slope of the curve at that specific point. So this is where we put a limit here. So we talked a little bit about limits in some of our pre-work. So the limit as h goes to 0, we're trying to make h as close to 0 as possible. We're putting h to 0. And when we can do that, then f of x plus h and f of x overlap. And then we'll find the slope at one specific point, which is a big deal. You should think about kind of the consequences of that. Now, this one says your turn, so you're going to have to do it. The hint I'll give you is written there, but I'll write it down again. X, f of x. So that's our stable point, our sticking point. Actually, I lied. Fix a f of a somewhere. A f of a. Because that's often how they do it in books. That's the only reason I'm saying that. And for funsies, I'm going to put x f of x over here. And what do you think you're trying to do with the value of x? Hint, it'll involve a limit. We'll see if you can get there. So now we have to go through a kind of hierarchy of situations. What does it mean for a function to be differentiable at a point? So differentiable, at a point. So what does that mean? Well, let's go back. What does it mean for a limit? Let's write limit better. Limit exists. So you should know this. You should be able to fill this in. A limit exists when, and you should be able to fill in the blank, but it's when x approaches a from the left for some function is the same as x approaching a from the right of that same function. That means the limit exists. The next step is when is a function continuous at a point? So when is a function continuous at a point? Well, the limit has to exist. So the limit as x goes to a exists, and it has to equal, you should know this, has to equal the function value. So the limit equals the function value. So that means we can't have a curve like this, and then an open dot, and then this, and have a closed dot down here. That's not continuous. The limit exists for that function, but the function is not continuous there. Now for the differentiability, well, let's see. For continuity, we need the limits to be the same on both sides. For differentiability, you need the limits to be the same, but the limits of what? The limit of the derivative. So I'm going to write that as f prime, which is simply a notation for the derivative. Now, right now, you are thinking of the derivative. Let me give myself a tiny more space. You're thinking of where f prime is equal to the limit as h goes to 0, f of x plus h minus f of x all over h. Okay, that's a lot. That's a big deal. And the yellow sticky note there says, okay, what about a differentiable from the left and differentiable from the right? So that's what these two pieces are. That's differentiable from the left. That's differentiable from the right. If those are the same, then the function is differentiable at that point. Okay, find the derivative. So I'll help with this one. So you start with the limit as h goes to 0. You may think you know some shortcuts. We're not allowed to use those yet. So f of x, it might be helpful to write f of x plus h here. So 2x plus h squared minus, that's not a 3, 3x plus h. So the limit of 2x plus h squared minus 3x plus h minus, now, be very careful. Don't forget parentheses here. You're going to forget it, and you're going to mess things up, and I'm going to forgive you, but try not to. So that's the algebra. Well, that's the setup. Now let's do the algebra. You should pause the video, and you should try to do it yourself, and then you should see if you get to the same work. So feel free to pause. And then I'm going to start writing. So here's my guess. You should have written this as x plus h times x plus h and multiplied that out. If you did that, you would have gotten this. If you didn't do that, you probably did bad math. I forgive you, but be careful. Minus 2x squared minus negative, so plus 3x, all over h. Now, so we have limit as h goes to 0. We're going to have 2x squared plus 4xh plus 2h squared. Now we have a minus 3x right there and a plus 3x right there. So those cancel out. Minus 3h minus 2x squared all over h. Now, notice how the 2x squareds will go away. So then we will have, I'll write it here, the limit as h goes to 0. We're going to have 4xh, 2h squared, and then 3h, all over h. Well, what can we do here? What we can do is we can take h's out of all those pieces. So if we, this isn't letting me do what I want, but that's okay. If we take h's out of all those things, then we're going to have the limit as h goes to 0, and it's going to be of 4x plus 2h minus 3, which as h goes to 0, what's 2h when h goes to 0? That's 0, so 4x minus 3. And that's your derivative. That's the first time you took a derivative by hand using the definition of the derivative. So now this says, find the derivative of this function when t equals 0. So try to set it up by yourself right now. Feel free to pause. Try to set it up. Okay, I'll set it up now. So the limit as h goes to 0. Now, we want t to be 0. So we can consider g of 0 and g of 0 plus h, because we're looking at a specific place. So it's going to be, I'll set up generally, 0 plus h minus g of 0 all over h, which is going to be the limit as h goes to 0. Be very careful with your notation. You need to have an h goes to 0 in all of these limits. And if you're going to say equality, you need to make sure you have the limit You just need to be careful. So g of 0 plus h is 1 over h minus 2. And g of 0 is 1/2, so minus negative 1/2 all over h. Now that might cause you some of you to worry, because we see fractions, but it's okay. Go ahead and get a common denominator. So multiply the first one by 2. And that's going to be h minus 2 times 2. And then multiply the second one by h minus 2. So that's 2h minus 2. We have a common denominator now. And we can say, okay, equals the limit as h goes to 0. It's going to be 2 plus h minus 2 over h. And if you multiply top and bottom here, if you multiply by that 2h minus 2 and 2h minus 2, those will cancel. And you'll wind up with it down here. So 2h, h minus 2. Notice how the 2's cancel on top. So you have the limit as h goes to 0. So you have h over 2h, h minus 2, which is going to be equal to, I'm writing equal, so you have to make sure these things are equal, so don't forget your limits. Your h's cancel, so that's 1 over 2, h minus 2. Now make h go to 0. So that's 1 over negative 4, or negative 1/4.